If you've been learning about material balances but still feel like you struggle when it comes to actual problem solving, you are not alone. If you're following a haphazard solution approach or repeating the same mistakes, it just reinforces bad habits. So, to fix that, today we are going to practice solving material balance problems step by step, applying our ultimate solution strategy. We looked at material balances of the total system in the last part, and in this video, we will focus on multi-component systems. Let's start with a very quick recap of the strategy. Read the problem carefully, then draw a diagram and mark what is given. Select a suitable basis, then start writing the equations algebraically. This may include material balances for the total system, for each component, or any other kind of equation based on the problem. We balance the mass flow rates if we are analyzing an intermediate stage of an ongoing process during a specific time period, and the total masses if we are concerned with the final result at the end of the time period or the end of the process. Make reasonable assumptions, then use mass representations to express the mass terms in the equation in the form of the provided details. After simplification, we substitute the numerical values along with the units and apply the necessary conversion factors. Finally, we perform the calculation and scale the answer to match the problem requirements. We are given two simultaneous ionic reactions. Reaction 1, the desired reaction. Ethyl acetate plus hydroxide ion react to give acetate ion and ethanol. Reaction 2, the undesired reaction. Methyl acetate plus hydroxide ion react to give acetate ion and methanol. The selectivity in moles of reaction 1 relative to reaction 2 is 1.081. The feed contains hydroxide ion at 0.1 mole per liter and 0.05 mole per liter each of ethyl acetate and methyl acetate. The final solution contains 0.023 mole per liter of hydroxide ions. How much methanol does the final solution contain? Alright, let's draw a diagram of our system and mark what is known. We will also write down the reactions. You must balance the reaction equation if it is not already balanced. A balanced reaction equation simply means that the number of atoms of each type are equal in the reactant and the product side. Let us know if you would like to learn more about how to balance chemical reactions. All mass quantities are already given in per liter, so let's just select 1 liter as our basis. Now, it's time to write the material balance equations. We have multiple components in this system, and we are concerned with just the initial and final state of the system, not what's happening during the process. So let's write the total mass balance equation for a multi-component system. Since the process is over and the system is no longer changing, the system is at steady state, meaning we can drop the mass accumulation term from our equation. Now we balance all of the components. We will represent mass using moles per liter, denoted by the square brackets, and simplify. As you can see, the number of unknowns is more than the number of equations, so we need to write more equations using the information provided. We can use the reaction stoichiometry. The ratio of the change in the number of moles and the stoichiometric coefficient is equal for all species in the reaction. For example, in reaction 1, the moles of ethyl acetate consumed divided by the stoichiometric coefficient 1 is equal to the moles of ethanol formed divided by the stoichiometric coefficient 1. We can also add the similar stoichiometric equations for the simultaneous reactions to obtain the combined hydroxide ion consumption. Think of it as writing the balance for each type of participating ion in this problem. We can also use the selectivity, which is the ratio of the moles of the desired product and the moles of the undesired product, to get an additional relationship. After further simplification, we substitute the numerical values with units and compute the unknowns to get our final solution. We have an industrial lemonade machine that takes up a feed comprising water, 7 liters per minute, lemon juice, 2 liters per minute, and syrup, 1 liter per minute, and mixes them to produce lemonade. Question 1. What is the density of the lemonade product? 70% water, 20% lemon juice, 10% syrup. We are given the density data. Sugar syrup 1.23 gram per ml and lemon juice 1.03 gram per ml. Question 2. Two new products are now introduced. Unsweetened lemonade, which is 75% water, 25% lemon juice, and lemonade concentrate, which is 55% lemon juice and 45% syrup. All three products have an equal production rate. What is the ratio of the flow rates of the inlet streams? Note, all compositions are in volume percentages. Like always, we'll first draw a diagram to represent the system. The machine is the system, the water, juice, and syrup are the inlet streams, and the lemonade is the outlet stream. Let's mark what we know. In the first part, flow rates and compositions are both known, so we can skip basis selection. This is an ongoing continuous process, so let's balance the mass flow rates. We are not concerned with the individual materials flowing in and out, even though it is a multi-component system. We are focused on the total material flowing in and the total material flowing out, so we can write just the equation for the total mass flow rate balance. No material is being consumed or formed, it is just being mixed in a specific composition. It's reasonable to assume that the industrial lemonade machine is operating at steady state since nothing in the problem indicates otherwise. We can make a standard assumption that the density of water is equal to 1 gram per ml. We are given the volumetric flow rates, so we will be representing mass flow rates as density times the volumetric flow rates. Now we can substitute the numerical values with units and apply the necessary conversion factors and solve to get the density of lemonade. For the second part, the system is different, so let's draw a new diagram. We know that the production rates of all products are equal, but we don't know the exact quantity. So let's take a 1 liter per minute production rate of each product as our basis for simplicity. We want to analyze each of the outlet streams separately, so we need to balance each component individually. Let's call our products P1, P2, and P3. All of the water flowing in is being distributed among the three outlet streams. Same for the other input materials. The system is at steady state. We represent the mass flow rate as density times the volumetric flow rates and cancel out the terms common in the LHS and RHS for simplicity. We can describe the volumetric flow rates of a component in the outlet streams using the composition data. Substitute the numerical values with units and compute the final answer. As we have seen, there can be many different kinds of reasonable assumptions we can make to solve a problem. If you are stuck on a problem, wondering if some information is missing or if you made an incorrect assumption, you might benefit from this table that lists possible helpful assumptions, when you can use them, and more importantly, when you should not use them. You can find the link in the description. Now that you know all there is to know about material balances and you have practiced all the concepts, let us know if you have any questions or if there are any concepts you would like to practice more. If you found this video helpful, hit the like button and subscribe to Exemplify to help us grow and to power up your learning. Thank you for watching.